let's move to the case study, because I want to try if this methodology could work in architecture. The procedure is simply to produce a cover. The cover measures 110 meters from that point, and you can see 4 yellow circles. These two big ones are the main pillars. The diameter is 5.0 meters, and the small ones are 2.5 meters. So only 4 points to sustain the entire structure. And because in Italy we have seismic action, I want to put a load that simulates seismic action. So we have 4 orthogonal direction where applied the seismic action. So the first point is to define the design space that is in light blue. The dark blue, the flooring slab, represent no design space, so we have a normal structure on the cover. The design space is the area where the topology optimization will work, and the columns are no design space, so we work only on the light blue volume. This is the animation of the results. So okay. Okay. As you can see, the material is covered. You have only the exactly quantity of material necessary to sustain the structure. Obviously, the result is a very high organical shape, difficult to be built, but we try to define a solution. So we have another sketch of the structure. It's very interesting how the support structure pretends itself to sustain the external area of the structure. Okay, this is the animation of the single pillars, the XN pillars. Okay, the result was on a solid model, and this is in the picture you can see the solid model. The surface is extremely irregular, and obviously it's not a very interesting surface for architects. So we had to work on processing the model, creating 400 cross-section to replicate the shape of the structure, and then to create a surface to define exactly the form. But we have a problem. This material is full of steel. So this is very, very heavy, and we are working in the harbor. So we have to create a more light structure. And in this sense, we create a latticed structure. This latticed structure is composed by 4 pillars. So we have 4 assemblies. First assembly, second assembly, third and fourth. Each one of these 4 assemblies is made by 3 different. Is made by 3 different components. So we have transverse closed ribs, longitudinal chords, and diagonal ties. So we create the structure to imitate the radius in this way, and then create a database with different cross-section. Put this different cross-section in the software, we run with a size optimization. So we have exactly the number of pieces and the section of the pieces to have the more lightness structure in the total respect of the stress of the standard. And to have a small number of sections, we create a small database, of course. So during the first step was a structure, and the weight was 441 tons, and the maximum stress in the steel section were lower than 150 megapascal. The the site optimization procedure reduces the weight about 30%, maintaining the same stress. As you can see in the picture, only one of the three components, in particular the rib, is the section of the rib is reduced. The other two components remain the same. So this variation represents that the stress remain in the same sections. And this is the final analysis of the structures. So the real result of my thesis is on the methodology. And to give an answer about the question of the previous presentation, in the green boxes there is the designer analysis phases. So the designer is the creator of the project because you choose the design space. In the orange boxes there is the analysis model. So you have to put your model in some software and some tools to help you to create the analysis model. And then you launch the topology optimization or other kind of optimization. And if the result is satisfactory, you can continue with a refinement of the shapes of the choosing of the material and create other analysis. The last analysis in this case is represented a site optimization. Then you can run with further verifies, and if the result is really satisfactory, your structure is complete. But my research is strongly oriented to the designer, to the control of the process by the architects, by the engineers, not only follow a CAD or CAA procedure. So this work has proposed a new design methodology to obtain efficient architectural structure by exploiting the capabilities of topology optimization. In the picture you can see some rendering for a challenge in Germany to present this project. So the strategy is based on 4 steps: the finding of the architectural structural form by using a topology optimization procedure, the definition of the latticed structure in order to reproduce the form previously found, the design optimization of the structural elements, and the verification of the structure subjected to standard design action. Only few slides to present some future developments of the procedure. The problem is move from concept to reality. So find a solution to build this interesting form. So now my tools are improved and the algorithm is more sophisticated, and I try a new challenge. So this is the working progress for a stadium design, but starting from a design space, a simple design space. This represents a quarter of the entire stadium. I get the result about the topology optimization, and then I try to define the stadium using a conceptual structure. So put some of my structural knowledge in the structure in the stadium to create an order of different columns to sustain the weight of the structure. And thank you for your attention.